Well, hello and welcome. We're so delighted to have you join us today. I'm going to have a few introductory slides as we let people kind of roll into the webinar, and then we'll get started with the main content. Just so you know you're in the right place, this webinar is entitled A Path to COVID-19 Recovery, How to Improve Indoor Air Quality When Reopening K-12 Schools. I just wanted to take a moment to recognize our supporters for this webinar, the UC Davis Western Cooling Efficiency Center and Johnson Controls. My name is Allie Loge, and I am the Director of Communications and Outreach for the UC Davis Energy and Efficiency Institute. Just so you know, this webinar is focused on the specific topic. We have a few just introductory remarks about our goals. The presenters today, who I'll introduce in just a moment, do not have an opinion or a position on when schools should reopen. The purpose of this webinar is really to share information on how to most safely operate building systems for schools that are reopening. Following these recommendations does not ensure COVID-19 spread will be reduced. We're just presenting the most recent research, which is still being investigated and changes, quite frequently. Other possible measures to reduce COVID-19 spread, like sanitation, social distancing, and masks, are not covered as part of this presentation. And going to our presenters, who you can see on the webcam here, we have Rengie Chan, Dr. Rengie Chan. She will be presenting first. She is a research scientist in the Indoor Environmental Group at Lawrence Berkeley National Laboratory. She will be speaking in the first part of the presentation on the importance of indoor air quality and ventilation. Our second presenter there is Theresa Pistochini. She will be speaking on implementing indoor air quality and ventilation solutions. She is the engineering manager at the UC Davis Western Cooling Efficiency Center. Just a little housekeeping, and then we'll get to the presentations. You are on mute and shouldn't be able to share your webcam. If you have a question or any audio-visual issues, please let us know in the chat or question box that you should have up on your screen. There will be time for Q&As at the end, about 10 minutes or so. Of course, there may be more Q&As, and we will follow up afterwards with answers to your questions via an email. So you will get a document with all the Q&As. There is a handout of this presentation, and it's in the handout section of the GoToWebinar. You should see it kind of in your screen or main menu. That is a PDF of the presentation where all the links are accessible or hyperlinked, so you should be able to click on any of the links the presenters are showing you. At the end of this webinar, we would really appreciate you completing our survey, where you can share your experience and join our mailing list. We will also submit an email probably next week to you that will show you the recording, have our presentation PDF, as well as answer all your Q&As. This recording will be available on our website as well as our YouTube channel. And with that, I'd love to introduce Rengie and let her take over the presentation. So bear with us as we switch here. Okay, Rengie, you should.
Right. So thank you for having me today. In my part of the talk, I want to give you an introduction of indoor air quality and building ventilation, what we know about ventilation and infectious disease transmission, and on student health and learning. I also want to make a very important point. We see guidance from CDC, and just yesterday, the Los Angeles County came up with their own version of what reopening schools looks like. And all these guidelines call for paying attention to having adequate building ventilation and outdoor air. But through decades of research, we continue to find adequate ventilation to be a common problem in school. So today I want to give you some background on what is known as a motivation to really address this problem. Now, indoor air quality is an everyday issue that impacts our health and well-being. During this pandemic, we worry about respiratory aerosols in addition to other indoor air pollutants of concern in classrooms. And this includes VOCs, formaldehyde emitted from building materials, cleaners, CO2, which is a biomarker of bioeffluents emitted by people. And in terms of outdoor air pollutants, here I'm showing you particulate matters that are emitted from vehicles, industrial sources, wildfire smokes, can also make its way indoors. There are three ways where outside air can make it to indoor air. One is through mechanical ventilation. The others is by natural ventilation through opening doors and windows, and also air can leak from outdoor to indoor through cracks and in the building envelopes. Now, among these three routes of bringing outside air to indoor, the mechanical ventilation route has the greatest potential as being a mean to control indoor air pollutants, because air can be filtered before it's entered indoors. It is also can be controlled using a fan and programmable thermostats. So in classroom that relied on natural ventilation, and we understand there are those classrooms that rely on those, adequate ventilation will rely on manual opening doors and windows by teachers, and also the amount of airflow will be dependent on weather. So ventilation may be inadequate at times. Now, classrooms often have mechanical ventilations, classroom in the US, and these are called HVAC system, the heating, ventilation, and air conditioning system. And you may find systems like this at your school. This is a rooftop unit. This is a wall mount system commonly found in portable classrooms, but also used in permanent classrooms. Here I'm showing you some blue lines of how outside air enters through the system and is brought inside the classroom. So if you have a window, it will go through your window from outside air to indoor air. And if you have a system like this, this is how outside air enters into classrooms. In second part of our presentation, Theresa will share with you recommendations on how to operate these systems safely as we open schools. But before we do that, you'll hear a lot of talking about CO2 in our presentations. We talk a lot about CO2 because it is a relatively easy way to measure ventilations. It is a mature technology. The sensor itself is fairly low cost. And here's what CO2 concentration looks like in an occupied classroom. So you have kids coming in, the concentration will begin to rise because of students exhaling CO2. And in our breath, the amount of CO2 is about at 4 or 5% level. So it's much, much higher than what our background level is, which is at around 400, 500 ppm, or 0.04, 0.05% of CO2. So as a result of that, we see concentration go up during the day, and then it'll come down when the student leaves. And when we see data like this, where the concentration over the course of the day was about 1100 ppm, it suggests to us that this classroom does not have adequate ventilation. Because if you have enough outside air to dilute the CO2 being emitted by students, we shouldn't see concentration this high. Now let's take a look at what school reopening guidelines says about building ventilation. And before I go there, I like to make the point that the primary route of the coronavirus transmission, as we know it, is through close contact, which is for that reason, we are all recommended to wear a face covering and maintain physical distance. But ventilation is mentioned in CDC guidelines. So if you go to the tool that they have developed, you can, within this box, I'm like scaling it up so you can read better. It recommends having good ventilation. And in particular, CDC guidelines says that you should ensure that ventilation systems are operating properly. You should increase outdoor air as much as possible, such as by opening doors and windows. But they also cautions that natural ventilation can bring in outdoor air pollutants and allergens that can pose a health risk. CDC also recommend that you make sure that it has adequate ventilation when you do cleaning and disinfecting. Now, before Theresa goes into more details about what these guidelines need to, how it works in practice, and she will mention another set of guidelines that is from the ASHRAE, which is a professional organization for heating, refrigeration, and air conditioning engineers. And then the ASHRAE guidelines go in much more details. So Theresa will go into that. But before we get there, I want to share with you some findings from research that studied the role of ventilation on indoor environmental quality, student health and performance, and infectious disease transmission. So through a study of visualization techniques, so this is shining a laser at the source, we can measure or try to illustrate how virus is emitted when people talk, sneeze, cough, and we can show that an infectious person can generate large droplets and small aerosols. So here's a video from a university in Tokyo that shows how two people talking at each other can generate small particles illustrated by these droplets. These are the two persons here. And you may have seen similar images from a recent NIH study. They use a similar technique, shining a laser through to visualize airborne droplets when people talk, and what difference does it make when they wear a mask. So it's important to point out that environmental factors such as relative humidity and other environmental conditions would affect the size of these droplets and how much and the viral loads of these particles. And this is still an active area of research. Another active area of research is what we call the airborne transmission routes. It is a research that my group at Berkeley Lab and others are trying to better understand. What's shown here in a schematic is a computer model from a recently published paper that tried to simulate two people standing directly face to face at each other. So they model what we call large droplets, so these are big droplets that can potentially land on a person's face, so eyes, mouth, nostrils, and that can be one route of disease transmission, so close contact of large droplets. Another route is through what we call short-range airborne route. So these two people are standing close enough to each other. The expiratory jet, so from breathing, you can put your hand in front of your mouth and you can feel the air movement. So that will propel the aerosols from one person to another. The authors then conclude that if you wear a mask, you can block this route. And so then what would happen is the particles may go through your body heat and enter into the room. And there are also other ways that these long-range aerosols transport can happen. As you can see that there's some particles will be leaving the jet and entering into the room. So what my group at Berkeley Lab, and here's a schematic of what the facility looks like, is trying to conduct experiments and computer simulation to better understand how factors like airflow distribution in a room, ventilation, filtration, combined with other measures such as physical distancing, can help minimize these airborne transmission of coronavirus in a different built environment. So it is true that there's still many open questions about COVID-19. There are some literature on the role of ventilation on airborne transmission. In 2007, following the SARS and also as concerns for H5N1 rose, a group of medical and engineering experts systematically assessed 40 studies, and they came to these conclusions. They found that among the 40 studies they looked at, 10 of them were very conclusive on the association between building ventilation and the transmission of airborne infection. They found that there is a strong and sufficient evidence to demonstrate the association between ventilation and movements in the buildings, the spread of infectious disease, including SARS. But they did not find sufficient data to specify what is a minimum ventilation requirements in schools, homes, and offices. Now, the experts came to these conclusions by reviewing outbreaks of an airborne disease that could directly attribute to a lack of outdoor air into circulation within an enclosed space. They also review evidence of airborne infections as a function of ventilation rate per person. So currently, there's still many questions about the infectious dose and source strength of the coronavirus. So we cannot assume that these conclusion is from this review is directly applicable. But given that there's sufficient concern over this airborne exposure to the virus, ventilation and other changes to building operations expected to help to reduce this risk. Finally, I think a lot of you may have heard about this study, maybe on the news, about this air-conditioned restaurant. I'd like to point out one point that maybe some news coverage may have missed. So researcher, after this outbreak, went back to the restaurant and did a site visit, and they found that the restaurant had no ventilation. The exhaust fans were turned off and sealed off. So the air conditioning system that you see, and these are 4 of them illustrated here, only provide cooled air that circulate in the restaurant. The researcher also looked at video recording to try to understand where people are sitting, and they release a warm tracer gas as a surrogate for the droplets that may be emitted by the patient, by the infectious person. So, and using a regression model, they're able to show that the higher concentration of tracer gas is associated with a higher risk of acquiring COVID-19. So these researchers conclude that the infectious distribution is consistent with a spread pattern representative of the exhaled aerosols. It is critical, they said, to prevent overcrowding and provide good ventilation in building. Now let's take a step back from the current urgency of COVID-19. My research group and many others have been studying the role of ventilation and filtration for a long time in classroom and other built environments. We know that ventilation is important in removing indoor emitted air pollutants such as VOCs, formaldehyde, and so on. We also know that filtration can be an effective control to lower PM levels indoors. Now, as coronavirus exists in droplets and aerosols, some of them are in the size range that can be removed by air filters. So, and in addition to vent the amount of outside air, well-designed air distribution system is also important. So to ensure thermal comfort of occupants. So people want fresh air, and they also want it to be not too hot, not too cold, not too noisy, and they don't want a whole bunch of air dumping on them all at once. Bill Fisk was a senior scientist in my group, and in 2017, he published a literature review titled "The Ventilation Problem in Schools." He concluded that there's compelling evidence from looking at many studies that there's association with increased student performance when you increase ventilation rate, and also you can decrease respiratory, reduce respiratory health and reduce student absence as you increase ventilation rates. So this work was sponsored by the Indoor Environments Division of US EPA. It's an important review, so I'm going to break it down a little bit more by going slide by slide with the findings that Bill found. Among the 11 studies that were reviewed, there is statistically significant, where here we define at 5% probability that observed outcomes due to chance. Improvement in some measures of student performance with increased ventilation rates. So these studies, some of them were based on student test scores on some standard academic achievement test. There are other studies that are done using a special test designed by the researcher to measure student performance. Among the 11 studies, there were 5 what we consider as strongest studies because they use an intervention approach where the researcher increase the ventilation rate and measure what the result is in terms of student performance. This could be done using a math task measuring speed and accuracy, logical thinking, reading and comprehension. And they found that in all 5 of them, a relationship between increasing ventilation rate and better student performance. There is also an association with health symptoms. So these are based on self-reported questionnaire, but also a few studies were based on measured signs of respiratory health. Again, as you increase ventilation rates, the health symptoms decrease. And finally, there's a limited number of sets of studies that look at the association between ventilation rates and illness absence. Among the studies, one that is conducted by my group, led by Bill and Mark Mendel, who's now at the California Department of Public Health, and they follow 162 classrooms over 2 years. What that study found is that the study recruited 28 schools from 3 areas of California. And the study collected illness absence data, demographic data, and our team also installed a CO2 sensor to monitor the ventilation rates over 2 years. The study found that all 3 school districts has a median ventilation rate below standard, an increasing ventilation rate from the current 4 liter per second per person, or about 8 or so CFM per person, to the minimum requirement of 15 would reduce illness absence among students. And further increasing ventilation rate would provide additional benefits. So you may say, this is great research, thanks for sharing, but that's not my school. We have HVACs, like the ones you show, and it turns on, it heats and cools, so things are working fine. I don't have to worry about this. Not so fast. So in a paper that Theresa and I published in 2019, our team visited 104 classrooms from 11 schools in California. They all recently retrofitted with new HVAC system between 2013 to 2016, so relatively new equipment. My team at Berkeley Lab, we monitor CO2 for 4 weeks in each classroom. We found that in 65% of the classroom, they had elevated CO2 concentration about the 1100 level, ppm level. Theresa led a field team that inspected these HVAC equipment. They identified a range of problems, hardware problems, these are inadequate ventilation equipment or improperly installed, fan not operating continuously, so these are control problems, so leading to not enough outside air being delivered to the classroom when it's occupied, and filter problem, filter that's past due or past service life and more than. And these problems are so common that more than half of the classroom have one or more. So before I hand the presentation to Theresa, I'd like to summarize what we just covered. I hope I convinced you that ventilation is really important as we reopen schools. It's an everyday problem, but in COVID-19, it's more urgent than ever to make sure that classroom ventilation are working properly.
All right, we're going to transition over to Theresa for the second part of our presentation. Thanks so much, Rengie. We're getting some great questions, so continue adding those, and we'll have a chance at the end to answer a few, and then follow up with you all later on the rest of your questions.
Okay, thank you. Can you share my screen? Can you see my screen, Allie?
Yep, it looks great.
Okay, thank you. Okay, so in part 2 of this presentation, we're going to talk about mechanical ventilation system recommendations with regards to rates, system commissioning, and system retrofits. Natural ventilation for the cases where mechanical ventilation is not available or inadequate. Filtration recommendations, carbon dioxide monitoring, and how to prioritize with limited funds and limited time. So most of the recommendations that I am presenting here today come from the American Society of Heating, Refrigeration, and Air Conditioning Engineers, or ASHRAE. The ASHRAE leadership statement says that transmission of SARS-CoV-2 through the air is sufficiently likely that airborne exposure to the virus should be controlled. Changes to building operations, including the operation of heating, ventilation, and air conditioning systems, can reduce airborne exposures. They have extensive technical resources regarding operating HVAC systems. What I've tried to do is comb through all that and provide you the information that I think is most relevant and most important. But I've provided the link here for you as well, and it's also being updated continuously. So this is the information as of when I went to bed last night. Okay, so as Rengie described, we have mechanical ventilation and natural ventilation. I'm going to talk about mechanical ventilation first. The big benefits of mechanical ventilation are that it allows for filtration. It's supplied by a fan, so it can be controlled through an automated system, and it can be integrated into a packaged HVAC system, or it can be standalone. Natural ventilation uses doors and windows. it requires manually, generally speaking, requires manually opening them. And it's quite variable depending on weather conditions and may not provide adequate airflow. There are also concerns with security and noise and comfort. So when we talk about mechanical ventilation, the question is, how much do we need? So I wanted to cover here building code requirements not related to COVID-19. But so we can see here, state building codes vary. A lot of state building codes are based on a standard called ASHRAE 62.1. Ventilation rates are reported in cubic feet per minute. So I've done some example calculations for you here for one classroom, assuming that that classroom is 960 square feet. And at the top of the chart, we can see an increasing number of people requires an increasing amount of ventilation for that classroom. So for example, ASHRAE would say for a classroom with 18 people, you would need 295 CFM. And for 35 people, you would need 465 CFM. California's Title 24 has slightly different requirements that result in larger amounts of ventilation, just slightly. And those are calculations that are based either per person or per floor area, and then you have to provide the amount that is larger. So in California, even if you have one person in that classroom, you need to provide 365 CFM, and then as you add people, the rate increases. But generally speaking, just to order of magnitude here, for a fully occupied classroom, we're talking in the realm of 450 to 500 CFM of ventilation for a classroom. So you'll see guidance from the CDC that, and from ASHRAE, you'll see suggestions to increase the amount of ventilation to the extent possible and potentially provide, the maximum outdoor air that you can. As Rengie pointed out, it hasn't been determined that there's any amount of ventilation that will make the building, for example, completely safe. And so really the exact benefits of exceeding minimum standards are unknown. There are some risks to increasing ventilation rates above those minimums that I showed on the previous slide. Equipment may struggle to meet loads above the design rates. Temperature and humidity problems may result. And energy consumption will increase because you need to generally condition all that ventilation air that you bring into the space. So I would recommend instead to commission your ventilation systems for your classrooms for full occupancy. Say that that classroom normally holds 34 people. Commission it to provide enough ventilation, or 500 CFM for those people. And then during I'm seeing suggestions that classrooms may be filled at lower capacities, and so to distance students. And in that case, you'll actually be providing more CFM per student. You can also encourage teachers to open doors and windows in addition to using mechanical ventilation when outdoor conditions are favorable and it's safe to do so. And then that will increase the overall total ventilation at times as well. I want to talk a little bit about economizers. So economizers are a device. So this is a cross-sectional sketch of an HVAC system. And this is the damper here, this black line that opens and closes to bring outdoor air into the building. And what an economizer does is that when its conditions are favorable outside, so say we're trying to cool the building, but outside it's 50 degrees. And so what this can do is open up the damper and bring in extra outdoor air when it's favorable to do so. This is a really great way to get extra outdoor air into your space and save energy. So particularly in drier climates like the West and the North, economizers can increase ventilation and significantly reduce energy used. I just also wanted to point out that economizer controllers are often available as retrofit products. I listed a couple of examples here. And so this is one thing that I would consider looking at if you're considering some HVAC retrofits, is to add economizer controllers. And certainly if you have existing economizer controllers, make sure they're working because they're really going to be beneficial in this situation. So operation of ventilation systems. It's recommended to operate your systems 1 week prior to school starting. 2 reasons for this. The first is to make sure that everything is functioning correctly. The second is to remove indoor pollutants that have built up over the course of these extended shutdowns. Also recommended is to flush the building 2 hours prior to occupancy every day at the maximum possible rate. Pre-COVID-19, this recommendation was 1 hour a day, so this has doubled. Ventilate during all occupied hours, that's always required. And then program and lock your fan schedule to ensure that teachers can't turn it off during the day to make sure the ventilation system is working all day. So for example, if your school hours are 8 a.m. to 3 p.m., you need to start your ventilation system at 6 a.m. And then you need to run it until the school is not occupied anymore. So for example, leaving some time for teachers and students to finish things at the end of the day and shutting off at say 4 p.m. It's really important to explain to teachers the purpose of the ventilation fan and that it must run all day and that it's bringing in outdoor air. A lot of times it's not understood, like when the heating and cooling isn't on, why is this fan still on? And that really needs to be explained so teachers understand that this is really a benefit to them and a safety concern, because it can be a bit of a nuisance. And so I think it's better accepted when it's understood that it has a purpose. So it's really important, as Rengie said, a lot of existing ventilation systems out there, they are capable of providing the ventilation that is needed, but they are currently not doing so. They really need to be commissioned. So many of your existing systems will be able to meet these requirements with the commissioning process. When you commission your outdoor air systems, you need to measure the ventilation coming into the building. So you can see here, this is just a picture of someone using a flow hood to measure the outdoor air coming into a wall mount unit. After you measure the air, you need to adjust and then retest if needed. I also wanted to just talk briefly about schools that may have existing demand control ventilation systems. I showed you earlier that picture of that moving damper. What a demand control ventilation system does is continuously control that damper to maintain a set CO2 target. ASHRAE is currently recommending disabling those systems. I'm very hesitant to recommend that because of the potential energy impacts and because these systems can offer a lot of benefits. So what I would consider as an alternate option is setting CO2 targets for those systems a little bit lower, such as 800 parts per million. And all of these systems give you the ability to monitor CO2 levels. So then use that to ensure that those demand control ventilation systems are working and keeping your CO2 levels below 1,000 parts per million. And then if they're struggling to work properly for any reason, you can always disable them and temporarily use them in a constant rate ventilation method instead, until you're able to get that system working correctly. In hiring outside agencies and contractors to do outside air commissioning, I wanted to recommend that you consider hiring contractors that are certified by one of these 3 major certification agencies, AABC, NEB, and TAB. And at this link here, we have a very detailed white paper describing those agencies and the benefits of using a certified contractor, and also comparing and contrasting them, and also giving you links to locate a contractor in your area. So what do you do for those systems that you either don't have enough ventilation, like you can't, there's no way that you can just recommission them, you need to add additional ventilation. I just want to point out that don't be too scared. There are potentially some solutions that are not that expensive. For any barred wall mount system manufactured after 1992, the ventilation devices are replaceable. So you can see in this photo here, this is where the outdoor air comes into this barred system. This essentially is a slot, and these ventilation systems that they sell for these HVAC systems are interchangeable. And you can actually, if you have a non-compliant system that can't be adjusted, you can buy just the ventilation device and swap them. So that's one really fairly practical way to increase ventilation in wall mount systems where, for whatever reason, the original ventilation device may not be capable. BARD has both what they call a commercial room ventilator and economizer. Both of those can achieve those recommended 400 or 500 cubic feet per minute of ventilation. And then definitely consider economizers in most climates in the US, the largest benefits being in the West and the northern climates. For packaged units from various manufacturers, Carrier, Trane, Lennox, York, many of those manufacturers have bolt-on retrofit economizer assemblies that you can use to add outdoor air to your system. It's going to depend, it's going to be very make and model specific. So I encourage you to ask your manufacturer, distributor about potential retrofit economizer assemblies. If none of these options are available to you, probably the next thing I would consider is using a dedicated outdoor air system, basically an HVAC system that's just providing outdoor air to those classrooms. And you can use one unit to serve multiple classrooms. Okay, so then if all that is, for whatever reason, you still can't get enough mechanical ventilation into your room, now what do you do? So I did want to point out that if insufficient mechanical ventilation is available, using your doors and windows is still a fairly decent option if you have windows on opposite sides of your classroom, and when you open the windows and the doors, you have at least 4% of the floor area open on the windows. So for example, a 960 square foot classroom would need 40 square feet of open windows and doors, which is approximately what you would expect to have. Again, there are some drawbacks here. Security is a concern. The air is not filtered. There may be noise and temperature fluctuations, and you've really got to work with the teachers and school staff to make sure they're opening those windows and doors 2 hours prior to occupancy and keeping them open all day. This is a small set of data, but I think it's fairly compelling. In our study, this happened to be 2 classrooms that we came across at one school where one teacher, every single day, as soon as he got there, he opened both of his windows and his door in a portable classroom. This is in Northern California. And you can see over the course of the week, this is the blue dots, his CO2 levels generally remained below the target of 1,100 parts per million. In comparison, you can see here, there was another teacher, always had the windows closed, most often the door was closed. And you can see here that room's CO2 levels were quite high, over 3,000 at times. Both of these classrooms had a little bit of mechanical ventilation, about 100 CFM, but it was clearly insufficient. And this was a high school with fairly large classes, like more than 30 students per class. So this, this can work, but requires a dedicated teacher to be opening these doors and windows, and then obviously all the other concerns that I mentioned previously. Okay, I want to switch gears and talk about filter selection. Rengie clarified that even though virus particles are small, they're often contained within droplets. And so some of them can be removed by HVAC filters. we're recommending, consistent with ASHRAE, to use MERV 13 filters or better, and use the deepest pleated filter possible, for example, 2 inches deep, to improve its effectiveness and to reduce the amount of filter changes required. So I want to point out to check the pressure drop of the filters that you are buying. There is a prevailing belief that MERV 13 filters are problematic because of their pressure drop and their resistance, and that a lot of times that they won't work in older HVAC systems. I really want to dispel this myth. This is not true in most cases. If you obtain pressure drop data for filters that you're considering buying, you will see that there are low pressure drop MERV 13 filters available, commonly available. So here's some data from the California Energy Commission. Highlighted in yellow are 1-inch deep filters that were tested. You can see they tested 3 MERV 7 filters and they show the pressure drop results. And then they tested 4 MERV 13 filters and they show the pressure drop results. And you can see that there are MERV 13 filters that have lower pressure drops than MERV 7 filters. And then the situation can get even better if you look at 2-inch deep filters, you can get even lower pressure drops. So really consider MERV 13 filters. They should work in almost any application, and obtain the pressure drop, look at the pressure drop of the filters you're buying, and compare it to the filters you have currently. You might be surprised. Install your filters prior to recommissioning and testing your airflow. That way, when you do that recommissioning, you'll be able to confirm that your airflow is sufficient. Ensure your filter rack is sealed to prevent bypass, and change your filters every 3 to 4 months. The longer, the more like the 4 months I would consider if you have the 2-inch deep filters. Going from MERV 8 to MERV 13 filters will admittedly double your filter budget. However, we're only talking about an increase of about $20 a classroom per year. So even though it's double, it's not an alarming number. But it can be, if you haven't budgeted for that, that can be an issue. And I also want to point out that the energy impacts of adding MERV 13 of filtration in central HVAC systems is pretty small. It uses the pressure drop caused by filters. It increases your fan motor power by 20 to 40 watts continuously when the fan is running. That's about the power consumed by a computer monitor. For your HVAC maintenance staff, I just want to point out that it's important to consider PPE for filter changes, which historically would be much less of a concern because it's possible that these filters could contain virus particles. So wearing a mask, wearing gloves, an N95 mask if available. I've seen some conflicting information on potentially spraying filters with disinfectant. So that's, I'm not sure I would recommend that. I would probably take that out of there. Bagging filters and disposing of them in the garbage, and washing hands, changing clothes, and showering after maintenance. ASHRAE is also recommending portable HEPA filters for each classroom. This is possibly helpful, but I want to caution it's not the highest priority. If you do decide to get portable filters, for example, maybe these are in classrooms that you can't have central filtration or something like that, then you want to achieve at least 2 air rotations per hour. That would be approximately 250 CFM of filtration for a classroom. And I wanted to recommend you look at the Energy Star ratings. Make sure the air delivery rate is greater than what you require. And take a look at the look for a high clean air delivery rate per watt. This can vary by as much as a factor of 3. And you want to make sure that you're getting high efficiency devices because these will be running many hours per day. And make sure you consider the cost of replacement filters into your purchase decisions. Generally speaking, getting those MERV 13 filters for your central HVAC systems is going to be much a a much greater bang for your buck in terms of the cost of those filters. Okay, so lastly, here I want to talk about CO2 monitoring. After you commission your ventilation systems and upgrade your filters, I really want to strongly urge you to consider CO2 monitoring for your classrooms. Long-term CO2 monitoring will alert you to ventilation problems. Indoor CO2 levels should remain below 1,100 parts per million in well-ventilated classrooms. There are a lot of CO2 sensing devices available in different formats. There are just dozens of solutions out there. There are CO2 sensing thermostats for building automation systems. There are standalone CO2 monitors, and there are indoor environment type monitoring systems as well. So there are a lot of options here. We're working on a supplemental some supplemental materials that are trying to compile a list of some of these devices. If you're interested in receiving that, you could, at the end of the survey, give us your information so you can get follow-up information from us. Also wanted to just have a note about maintaining temperature and humidity in your spaces. Maintain temperatures recommended by ASHRAE of 68 to 78 degrees Fahrenheit. I did want to recommend that, generally speaking, districts limit cooling and heating set points to teachers to save energy, which is great. Considering our current situation, you might want to consider allowing teachers to have a little bit more control over their cooling set points, because often that's the biggest complaint in classrooms. This could potentially be more tricky if teachers are wearing masks or students wearing masks, and so you may want to allow for a little bit more comfort on the cooling side. Maintain relative humidity between 40 and 60%, because this has been shown to reduce virus transmission. In the event that humidity is low, which is unlikely, because generally in highly occupied classrooms, you can have fairly high humidity, but if humidity is low, you're going to want to check and repair your cooling system. And if it's still low because you're in a very dry outdoor environment, you could consider portable humidifiers with a humidistat. If humidities are too high, again, look into what's going on with your cooling system. Many of those, all those CO2 monitoring solutions that I suggested, generally speaking, also have temperature and humidity monitoring as well. Last note here about UVC lighting. There have been a lot of questions about this. UVC is a shortwave ultraviolet energy that's used to inactivate viruses and bacteria. One option is to install it inside of an HVAC system. So I want to caution you, this can be effective at sterilizing indoor coils, but it generally does not have sufficient exposure time to kill airborne viruses because the air is moving past that light at a very high speed. And so you would need extremely high power densities in order to be effective inside an HVAC system. UVC lighting may be more effective in ceiling mounted applications, but it's not widely tested in schools. This is a picture from an article in the New York Times, where basically they have some UVC lights in the corners here that is shining up towards the ceiling and creating essentially upper room radiation, and then they're using a fan here to draw the air up towards the top of the room. And so this has not been widely tested in schools. It requires maintenance and electricity. And if your school was to look at something like this, I just really want to stress that ensuring ventilation and filtration are adequate is the absolute highest priority. Although something like this may be effective, we don't really know. It's costly, and this essentially should be the last thing you do, not the first thing. So I just wanted to talk a little bit about that. Finally, make sure to pay attention to your restrooms. You should be running your restroom exhaust for 24 hours a day. you should have 70 CFM of exhaust per toilet. And also you want to test these ventilation systems as well and make sure that they're working. And bathroom exhaust fans are fairly straightforward replacements if needed. Also, there are recommendations for a nurse's office or where sick children wait to be picked up. It should have a dedicated HVAC system so that you're not circulating that air to other spaces. Ideally, it should have its own restroom. That restroom exhaust should exhaust directly outdoors, and you should try and maintain a negative pressure to your adjoining spaces. If you're investing in portable air cleaners, the nurse's office would be a really high priority place to put one. And finally, prioritize. So highest priority, test and commission your existing ventilation systems. If needed, repair, replace, or add mechanical ventilation. Consider use of doors and windows as a supplement, or if no feasible alternative. Install MERV 13 or better filters in your central HVAC. Consider portable air cleaners if adequate central filtration is not possible. And then third, monitor indoor air quality, carbon dioxide, temperature, and humidity, and make corrections wherever you notice problems. Okay, that's it. Oh, and here's a list of sources as well, and how to contact us.
Great. Thanks so much, Theresa. We are getting a ton of questions, and we have time for as many as we can do. So I will read a few I've been kind of going through, and Rengie's been looking too. We will go through and answer as many as we can. And as I mentioned, if we don't get to yours today, we will follow up and make sure that all of the questions are addressed as best as we can. Rengie, are there any that popped out to you, or do you want me to ask a few? Nope, I can't hear you. There we go.
I'll go ahead and answer two that I found.
Okay,
and
great.
By two means there might be more questions that asking about similar things. So I mentioned that there are only 10 of the 40 studies that were conclusive. So what happened to the other 30 studies? So these are studies of outbreaks. It's really difficult to go back and trace what happened and to meet the high standard of data quality and scientific methods required. So a lot of these studies are called partially conclusive, so that we can really rule out other factors that were just not measured or not able to reconstruct. But this brought out a good point. You all have heard a lot of outbreaks that we are facing in senior living settings. So some research ideas that we have is to see if we can go visit some of these facilities and measure ventilation rate and see if we can find a connection between ventilation rates and the spread of COVID-19. So it is definitely an area of active research, and more needs to be done. Another question that I want to answer is MERV rating. Theresa has mentioned MERV 13, but what about MERV 11? Is that good enough? So I want to mention the virus itself is about 0.1 microns in size, so very small. If we cough and talk, the droplets have a range in size. Typical range is between 1 and 100 microns. So a lot bigger than what the virus itself is. And the most is about 10 micron, but it really depends on what you're doing, what you're talking, you're coughing, you're sneezing. And beyond just the particle size, what's also important to consider is the viral load in these particles. So it is possible that the smaller aerosols are actually more important because they carry a higher load of the virus, and they're breathed into deeper lungs. So they're the ones that we really need to pay attention to. And those are not known right now. So, which is why we think that the idea of recommending MERV 13 is because we are, at least in California, quite familiar with it. New homes are required to have MERV 13 air filters. Some school districts, like with poor outdoor air quality, also recommended or required to have MERV 13, which is why we pick that filter to be a MERV rating to be what we're targeting. Theresa or Ali?
Yeah, I'll also add that the MERV 13 is consistent with the ASHRAE recommendation. They're also widely available and fairly comparable in cost to MERV 11 and similar in pressure drop. So I recommend that you get MERV 13 if it's available.
Great. We had several questions about bipolar ionization. Do either of you have any recommendations regarding that?
I'm not an expert on that, so I'm not going to answer here. But in our response, I will, we can come up, we can follow up with more what the literature is saying about that.
Great. Here's a question. Although we don't know exactly how much ventilation is needed to reduce transmission, is it scientifically supported to say that more ventilation is good?
I think so. I mean, I've shown you one of the study of the 2-year study. As you can show, as continue to increase, we continue to predict higher benefits from increasing in ventilation rates. So more is better. And one thing to point out is I mentioned that the LA County recently, just yesterday, came out with their guidelines. So if you design your system to be at full capacity and you have only 16 students, you already have almost double the ventilation rate per person. So that's a great direction to be heading.
The thing you have to be careful about is when you try to achieve that additional ventilation, what other problems you could possibly create with your HVAC system as far as thermal comfort or humidity levels that are too high or other issues. Like say you have someone commission all your ventilation rates to be very high, and then you get so many teacher complaints that your maintenance staff comes back and starts closing them all, for example. So just depending also on where you are, you know, if you're on the California coast and it's 70 degrees all the time, you know, great. But if you're in Florida where it's hot and humid, that may be much less practical. So sort of our overall recommendation is just to at least bring up those ventilation rates to that 15 CFM per person for a full classroom. And then if your classrooms are half occupied, you're essentially getting more like 30 CFM per person, which is quite good. And you know at least your equipment can keep up because it was designed for a 30-person classroom.
Yeah, one of the participants also mentioned just the energy costs, you know, associated with running, pulling in a lot of outdoor air. So that's another, lots of bad things to balance, but that's another thing people have to consider.
Yes.
Let's see. Another question. In many California schools, the mechanical ventilation is accomplished with fixed HVAC units that have fixed OA dampers, no economizers. In urban areas such as LA, air quality is also poor. How do you recommend an increased ventilation in these cases?
So most of those fixed ventilation devices you're talking about, they're actually manually adjustable. They have little dials that can change what that damper position is when it opens. And so I definitely recommend looking at that and commissioning and adjusting those systems. And then we've shown in some studies in fairly poor air quality areas that using MERV 13 filters reduces the particulate matter indoors by like 40%. So again, making sure you get that ventilation into the classroom and then using MERV 13 filters is recommended in California. So we can share more on that later if you're interested. But those recommendations still hold even in areas with poor outdoor air quality as well.
Great. And this is another question specific to many schools. Is there any guidance that mentions HVAC operations in buildings with plenum returns?
I'm not totally clear on that question.
Okay.
Often, I mean, a ducted system will have a return plenum, but that doesn't necessarily change any of the recommendations I made. Maybe I'm not clear on that. Maybe send a follow-up email. We can talk about it more.
Great. We have time for just a couple more quick questions. What is the rationale of running the restroom exhaust fans 24 hours a day?
That's a good question. That's ASHRAE's current recommendation. I guess the potential concern is that there might be restrooms used potentially after hours, you know, if they're not locked or something like that. And I think one of the other issues is just to get as many air changes per hour when that restroom is closed and not in use to make sure it's essentially ready for the next day. However, if you're confident those restrooms are empty and that building is locked, I don't think it would be unreasonable to shut it off at the end of the day, as long as you restart those fans 2 hours before the restroom's expected to open.
And that, I mean, if you run it all the time, you put that space under negative pressure. So there's, even though in the middle of the night, there's no potential of any leftover aerosols to leave that space into contaminate the rest of the building.
Great, and final question, does air direction in the classrooms matter? Like which way the air is blowing or how that's set?
Yeah, there's a potential concern about that as far as like where a potential sick student might be sitting in relation to other potentially healthy students and how the airflow is distributed. One thing, it's going to be extremely difficult to do anything about that in existing systems. The one thing I would recommend is that when you commission your systems, you make sure that your supply air is balanced. So say you have 4 supply air outlets, right? Make sure they're all distributing about the same amount of air so that you don't get, for example, higher velocities in one part of the classroom and lower velocities in another part of the classroom. I've seen some classrooms where you only have 1 supply air discharge, and often that can have pretty high velocities out of it. Usually it's towards the ceiling, so it's less of a concern, but I wouldn't sit a student anywhere that there's, you know, like a high velocity air discharge. But I think it's pretty difficult to do much about those situations in existing classrooms, and we don't exactly know what the benefit would be either. So I think you can use a little bit of common sense there, but that's about all the guidance we have on that.
Sounds great. Well, that brings us to the end of the hour, and we wanted to thank Rengie and Theresa for their great presentation and sharing this information with everyone. And thank you all for joining us. We hope it was informative and useful. As you leave, please be sure to take our quick survey. We will follow up with you with an email that has the Q&As that we didn't have a chance to answer. Our contact information is here on the screen. We'll also share our recording as well as the handout PDF of the presentation. Thank you all so much. Be safe and be well. Take care.
Okay, bye.
Bye.